Once more, have you ever considered what our sun looked like when it was an uncommonly energetic star? The James Webb Space Telescope has made a stunning disclosure about our star. For the first time, we can see our star in an entirely unique light. The JWST's most recent exposure offers enchanting insights into the youthful times of stars and the enormous cycles that could have happened in the beginning phases of our sun. Have we now opened another of the great secrets of the universe because of the new James Webb Telescope? What secrets still await us out there in the universe? The James Webb Space Telescope is a perfect representation of the advancements made by cutting-edge technology since the telescope was launched. The exploration of the universe has progressed at a quick pace. With its latest mission, the JWST has shown its magnificent capacity to dive deep into the mysteries of the universe. Indeed, the telescope demonstrated its absolute technical superiority when it imaged the object HH21 with incredible brilliance. HH21 is also called a Herbig-Haro object, a very young star yet advanced enough that it's blowing solid planes into the universe and starting to shape its environment since its observation by the JWST. The object has provided an overflow of important data about the young period of stars and, consequently, the early stages of our own sun. These observations equip us with pivotal information about the processes that happened during the initial stages of stellar development. Herbig-Haro objects are among the most captivating astrophysical phenomena in regions of young stellar development. They consist of narrow jets of gas shot out from newly formed stars, streaming into the surrounding interstellar space. At high rates, these jets crash into surrounding gas and dust, resulting in dramatic emissions. Herbig-Haro objects were discovered in the 1950s by astronomers George Herbig and Guillermo Haro, who were independent studying star-forming regions and first noticed the significant surges well before the JWST era. The energy-rich jets from the center of a young star were surprising. Who would have thought things would be so violent in the stellar nursery? Young stars are anything but cuddly. They are undoubtedly beautiful, but also incredibly powerful. We can hardly imagine the forces at play here with our minds alone. The forces that lead to the development of a star are immense, and even in the early billion years, things heat up around a young star. It takes countless years for a star to ultimately shine as serenely and steadily as our sun. The object of the latest observations, the Herbig-Haro object HH21, is located in an active star-forming region in the Perseus constellation, about 1,000 light-years from Earth. HH21 is particularly fascinating as it is one of the youngest and closest examples of these objects, making it an ideal field of study to research the physics of star formation. The discovery also provides us with stunning views of the dynamic processes that likely happened in the early stages of our sun's life. The JWST has imaged the Herbig-Haro object HH21 with remarkable precision, offering even more enchanting insights into what was previously difficult to see. For the first time, it may even be possible to see a double star forming at the center of HH21. The pictures reveal two bright, high-energy jets emanating from a single point. These jets are enriched with particles like carbon monoxide and silicon monoxide and are evidence of high-energy processes within the star and its immediate environment. The discovery of atomic hydrogen inside the jets was a significant surprise and now provides a completely new picture of the chemical structure and thermodynamic conditions in the early stages of star development. The surrounding accretion disk of the young star, along with various objects like planets and moons, could also form However, the intense radiation from the jets might make the formation of stable bodies more challenging. Nevertheless, the JWST observations also showed that the jets of HH21 are slower than those of many other Herbig-Haro objects. This slower speed could indicate that the star is at an early stage of development, or that the processes in this young system are generally less violent than in other stellar nurseries. The ability to observe such key cosmic processes up close and with high accuracy represents a significant advance in cosmology and will lead to even more astonishing discoveries in the future. Observing the birth of new stars also provides insights into how ionized gases and plasma interact. The fiery jets that influence the cold surrounding interstellar medium create brilliant shock fronts that act as visual boundaries of the young star systems. These early outflows of a star are much like the protective shell of our sun's heliosphere. On a scientific mission with the JWST, researchers are excited about the additional possibilities. The JWST is equipped with a range of innovative scientific instruments, including the near-infrared camera NCAM, the near-infrared spectrograph NSPEAK, the mid-infrared instrument MIRI, and the fine guidance sensor FGS. These instruments can detect even the faintest light from very young and distant objects that would otherwise be invisible to our eyes. By using infrared technology, astronomers can now see through dust cloud to reveal previously hidden corners of the universe and gain direct insights into young stars and their formation regions, often obscured by thick dust shells. Due to the high sensitivity of the JWST, astronomers and space enthusiasts alike can enjoy a level of detail that has never been achieved before in the history of cosmology. The JWST can not only image these faint light signals, but also analyze them. Never before have researchers been able to observe such detail to the vast jets and perform precise studies, providing information on the development and temperatures of the gases, as well as details of all the chemical elements and molecules involved. Herbig-Haro objects typical of dynamic star-forming regions like the Orion cloud or the Perseus cluster are crucial for studying chemical cycles in space. These regions are rich in gas and dust, providing ideal conditions for star formation. Stars are formed from the collection of these assortments of matter impacted by forces. The jets ejected by young stars which travel through space at speeds of several 100 km/s are only a part of the dynamic processes that occur during stellar development. When these jets impact the surrounding medium, they heat it up and create the characteristic bright arcs and knots visible through our telescopes. Within this visible display, enormous physical forces are at work, as well as a light demonstration of the components, along with electrical and magnetic forces. Fascinating observations reveal how the jets interact with the surrounding material, helping to shape the cloud from which the star is formed. Each light wavelength and each color gives the JWST, and thus the researchers, valuable clues about what's happening here. Observing these processes live and in their early stages is like getting a direct look into the blueprint of a star. If we understand how matter is incorporated into the larger cosmic cycle, how the final mass of a star is determined, in which elements and gases are involved, we can make significant inferences about the forces at work. This, in turn, helps us understand the broader matter formation processes in the universe. Although we can imagine that star formation is one of the great energy processes known to humanity, it is hard to grasp that such a young star can produce winds extending several hundred light years and blow them into space. The jets of the Herbig-Haro objects could be direct remnants of the immense physical energy that causes dust clouds to begin to rotate and coals in the center. Nevertheless, it is possible that the young star uses the jets to expel the forces it no longer needs while simultaneously driving developmental processes in the gas and dust cloud and star systems up until now we have only observed jets in young and actively forming stars. However, we are also aware of very old galaxies in the universe that also produce powerful jets in their centers. Some of these vast jets stretch far beyond their galaxies. These winds also scatter vast amounts of material, which ultimately influences the mass of the star and the environmental conditions of the star-forming region. The material and energy ejected then drive further starbursts or other processes in the universe. We should consider briefly the role of magnetic fields around a young star. Magnetic fields are essential for controlling the accretion process in which the star attracts gas and dust from the surrounding environment, and they also influence the direction of the jets. Magnetic fields are not only important in the immediate vicinity of young stars, but are present throughout the universe. These invisible forces direct the paths of charged particles and affect the shape and evolution of entire star systems in our own solar system. The magnetic forces mediated by the sun's magnetic field are vital for maintaining the heliosphere, the bubble that protects the entire solar system from harmful cosmic rays from interstellar space. The sun itself generates a complex and variable magnetic field that determines the order of our planetary system, impacts planetary atmospheres, and governs space weather patterns. Sunspots, solar flares, and coronal mass ejections are indications of the sun's magnetic activity. As you may know, such events sometimes significantly affect the operation of satellites and communication systems on Earth and produce auroras. The study of magnetic fields in young stellar systems like HH21 is an exciting field of research and is still in its early stages. If we understand the development of stars in distant regions, we can also gain insights into the history of our sun. Our star is 4.5 billion years old and has undergone many changes since its birth. In a dust storm and gas, the origins of our sun helped determine how planets were formed, from the gas giants like Jupiter to the rocky planets, including Earth, as well as smaller bodies like Mercury and Pluto. They were all in some way present in the early stages of the system, or their distinct conditions helped shape the form of the planets and subsequently the vast climate. The study of the universe through advanced telescopes like the James Webb Space Telescope opens windows into the deepest corners of space, revealing phenomena that were previously invisible or poorly understood. With its cutting-edge technology and exceptional capabilities, the JWST represents a leap forward in our ability to explore and understand the universe. One of the most captivating aspects of JWST observations is its ability to look into regions where stars are in their earliest stages. These stellar nurseries scattered throughout galaxies are vast laboratories where the process of star formation unfolds. It is crucial to understand this process because stars are not just celestial objects, they are the fundamental building blocks of galaxies and the sources of the elements that make up planets and life itself. The JWST is instruments such as the near-infrared camera and IR cam and the near-infrared spectrograph and IR are specifically designed to detect faint infrared signals emitted by young stars and their surrounding environments. Infrared radiation is particularly useful for studying these regions because it can penetrate the thick dust, clouds, and gas that obscure star-forming areas, revealing the hidden processes within. One of the key phenomena observed by the JWST is the accumulation of material onto young stars. As a young star forms, it gravitationally attracts surrounding gas and dust, creating a rotating disk known as an accretion disk. This disk is a crucial stage in stellar development as it provides the raw material from which planets eventually form. The JWST ability to study the chemical composition and dynamics of these disks sheds light on how planetary systems like our own solar system might have appeared billions of years ago. In addition to studying individual stars and their accretion disks, the JWST also investigates the broader environment of star-forming regions. These areas are rich in subatomic gases like hydrogen, carbon monoxide, and water vapor, which serve as the fuel for star formation. By mapping the distribution and abundance of these molecules, astronomers can piece together the complex processes that govern the birth of stars and the formation of planetary systems. JWST observations have also provided new insights into the role of magnetic fields in star formation. Magnetic fields play a crucial role in shaping the dynamics of accretion disks and controlling the flow of material from young stars. Understanding how these magnetic fields interact with the surrounding environment is essential for developing a comprehensive model of star formation and evolution. Perhaps one of the most spectacular phenomena observed by the JWST is the outflow of material from young stars in the form of jets. These jets, which can extend for thousands of light years into space, are driven by intense magnetic fields and gravitational forces near the stars' poles. Studying these jets allows astronomers to probe the inner workings of young stars and understand how they release energy and momentum into their surroundings.